Yeah.
All right, so on this assignment, on that big assignment you all handed in the other day, there was a question on, it was question number 24, which was missed, but it's still going to be a large number of times. So here's what you've got. It says, you in the strength and direction of the electric field in the position indicated by the dot, specify the direction as an angle above or below the horizontal. So, because of the fact that you're trying to find the electric field, which is KQ over R squared. So the trick here is that since both of these are positive values, so if this is a positive test charge, that field is going to be pointing in this direction here, and it's going to be, this field is going to be pointing in this direction here. So if you were to draw those like on a tip-to-tail method, you'd have something like this, okay? Now, since these are 5, 5, and 5, that means conveniently, that's going to be a 45-degree angle, right? Okay, this is 5, 5, and 5. So if you're going to use, there's a couple of ways you can do this problem. If you want to go smash mouth physics, so the trick here is that this distance here, okay, that you're going to use in this calculation has to be basically like the hypotenuse of this triangle that's 5 centimeters by 5 centimeters. Okay, so if you look at this in terms of the Pythagorean theorem, that hypotenuse is going to be 0.05 meters squared plus 0.05 meters squared. And then you're going to take the square root of that, okay? And then that's going to get you that distance between this charge and that charge, which is also going to get you the distance between that charge and this point, okay? Now, so if you go through the math, right, and depending upon how nerdy you want to get, okay, because it's a 45-degree angle, so it's like root 2, right, if you remember like your trig functions. So the other thing that you can do is you realize, well, you're going to take, you could find the square root of this whole thing, but then you're just going to square it again because of the fact that it's going to be KQ over R squared. So then, if you realize that that's going to go in there, then it's just going to be 0.05 squared plus 0.05 squared. Because if you take the square root of it, you're just going to square it back in, you're just going to get that number, okay? But here's what you have to realize. That's just this force. What you need are the x components of each one, because the y components are going to cancel each other out, okay? Because you're going to have one y component going up and the other y component going down. So if you can find one x component, then just double it, because that's going to be the same x component as the other one. So that went way south for some of you, okay? Because I honest to God, I don't even know what math you were doing, okay? Because it got real weird real fast, all right? So so when you get that back, if I have like random question marks written on your paper, because I have no idea what you were trying to do, and your answers were way off. So anyway, so just wanted to clarify that, because that's going to be important in terms of some questions on the assignment today. So, all right, stop that while I hand back those. Okay, so if you want to plan ahead, so here's what I know for certain, is that today we're going to finish up chapter 20 on electric fields. Review on Monday, have the test over electric fields on Tuesday, okay? So next big test is going to be on Tuesday. So what I haven't decided is whether or not I throw in a day of electrical potential energy, which I think I might on Wednesday, but then we'll review on Thursday and then have the midterm final on Friday. Right now, that's kind of what I'm leaning towards, okay? So, because electrical potential energy we can kind of cover in a day, it isn't that big a deal. All right, so let's talk about that sheet of paper, that single sheet assignment from yesterday. So, and this is what you have to keep straight, is the difference between an electric field and an electric force, okay? They're related, but they're not the same thing. So if you look at what's happening on this whole problem, is that you've got a charge here, you've got another charge here, and they're just giving you absolute value of 4 times 10 to the negative 6 coulombs. 1.7 times 10 to the negative 6 coulombs. And then some charge up here, which you know to be positive 1.0 times 10 to the negative 6, okay? So on this one, the whole key to this is that the magnitude of the charge of Q1 is known to be 4, the magnitude, okay, but the other signs are not. Determine the size of Q1 and indicate the correct signs below. So the whole key to this is that the electrostatic force on a student charge and the other two is measured to be entirely in the negative x direction. So what that means is that that force, the only force that you're going to have, the net effective value, is going to be in the negative x direction. So what's the only way that can happen? What has to cancel out?
Y's.
Yeah, you got to cancel out your y's. Okay. Now here's the deal. What allows me to actually calculate the force versus calculating the field? Yeah, I know what this charge is. If I just said, hey, just calculate the value of the field, all I'd have to have are these two values here to calculate the field. But since I have the charge, then I can calculate the force acting on it, okay? And that's the fundamental difference, is that I don't have to have the charge to calculate the field, but I have to have the charge to calculate the force. It's analogous to this. If I can drop an object and I can measure that acceleration, oh, that's 9.8 meters per second squared, okay? Whether I drop a chunk of stone or I drop a bowling ball or I drop page, doesn't make any difference. They're all going to accelerate at the same rate. Now, to actually calculate the force, I'd have to have the mass of page, or I'd have to have the 1 kilogram mass. So every potential thing that you could put in here in terms of a charged particle would experience the same field. But that doesn't mean that they're going to have the same force, okay? So no matter what I would put in there, that would have a certain strength of field. The force is going to be determined by the charge that I put there. Just like everything is going to accelerate at 9.8 meters per second squared. But I'm only going to measure force when I know the mass that's being affected by that gravitational field. So a gravitational field and an electric field are very similar to each other in terms of how we view them. Okay? So that's what allows me to calculate this force. So that if you think about this, all right, you know that this is a positive value. So what you're trying to figure out is what has to be the charges of those down below. Because if this is wrong, everything else is going to be wrong. So Cassidy, what do you have as your charge on Q1? Positive or negative?
Negative.
Fantastic. Mr. Cole, what do you have in your charge on Q2?
Positive.
Positive. Okay. Because if that's wrong, the rest of this problem is just going to end up being a train wreck. Okay? So Q1 should be a negative value, Q2 should be a positive value. Because what we're trying to do basically is we're saying this force is going to go this way, this force is going to go this way, your Y component is going to cancel out, you're going to have a net effect of a force acting in that negative X direction. Okay? So that's what you're looking for on that. So, when you get to that question on D, where it says calculate the magnitude of the calculate the magnitude of the force on the electrostatic on part 3. So on 3C, there's 2 ways that you can do that, depending upon what you want to do. But whether you want to find like the X and Y components, okay, or if you notice that that's a 37 angle and a 53-degree angle, you add those together, that gets 90. That means that top number is a 90. The other thing that you can do is just, the simpler way is just to work it as a triangle with the Pythagorean theorem, and you know that your 2 forces are going to be the 2 sides of the triangle. But no matter what, that overall force should make a not so good GPA, okay? Not absolutely horrible, but a not so good GPA times 10 to the negative third, okay? Anyway, so there's that. All right, any questions on that page? Going once, going twice? So make sure that gets handed in. Okay, stop that. All right, so if you look at kind of what makes your modern life possible, one of the key things you have is a parallel plate capacitor. And every time you use your phone, you take advantage of a parallel plate capacitor. So a parallel plate capacitor somewhat functions as a battery, okay? The whole point of a parallel plate capacitor is that it stores energy. So you can view a parallel plate capacitor as storing energy like behind a dam, okay? So if you look at this analogy of storing water behind a dam, so if you're going to store that water, then you have to somehow lift that water up and over that dam. And then as you do that, you store energy. Then that energy gets released back down once that water flows. But you have to do work to lift that water up. And so this is actually one idea of storing energy out of renewable energy sources like wind turbines or solar power. Because that's always the knock on wind or solar. It's like, okay, great. Solar panels work great when it's sunny. They kind of suck at night, you know? So the idea being is that you take that excess energy that's being produced by a solar array, you use it to drive an electric pump to pump water, and you store that water behind the dam. Then at night, you let that water flow back out. As that water flows down, it hits a turbine, spins, and that generates electricity, and you use that to generate electricity. Then the next day, oh, we have excess energy from the solar, you pump that water back up. So that's actually more efficient than a battery. The other idea, and this is my favorite, is that you have an autonomous crane, and you have big chunks of literally like chunks of concrete, like concrete blocks. So what happens is it's the same idea. You take the excess energy that's being generated by wind or solar, and then that crane grabs a hold of these blocks and it stacks these blocks up during the day. Then at night, it grabs a hold of those blocks, lowers them back down, and then as it's lowering back down, you're taking that potential energy and storing it and then converting it back into electrical energy. And those are actually, like both of those systems are more efficient than batteries and are actually cheaper. But the problem is they're not as cool. It's like, oh, we want batteries. Well, whatever. But that's the whole point. So what a parallel plate capacitor does is that it stores energy. But it's a very similar idea in the idea that you have to do work. So what I have here is a capacitor. Capacitors are rated, and we'll spend a lot more time talking about capacitors. Okay, this is just like an introduction because it's relative to electric fields. So what a parallel plate capacitor does is that typically the math works out as you have two plates that are something like this, okay? But what they found is that that's not very efficient in terms of like building something. So basically what they do is they take those parallel plates and they wrap them up like a jelly roll like this. And you put them into a device like this. So when you have your phone, for example, your phone has a whole bunch of capacitors, and those capacitors act as a storage device, and they store energy. So just like any electric field, you're going to have a positive and negative value. So one of the things that we'll start to talk about when we get into circuits, we're going to use this. It's called a voltmeter. So voltage is basically a measure of how much energy there is per coulomb. So to operate a voltmeter, you measure, and we'll get more into the terminology later, versus something in series versus something in parallel. Well, the terminology when you talk about a voltmeter is that you measure the voltage across 2 points. And that's pretty simple. So I've got my capacitor right here. And all you have to do is touch one side and then touch the other. So, and if you ever hook up a voltmeter and it goes in the negative region, just switch your leads around. So right now, this is sitting here, and this has a voltage of about 1.5 volts. So I have about 1.5 volts stored right now in that capacitor. So what I'm going to do is that I'm going to hook this thing up to this handheld generator. So as this spins, okay, what that's doing is that that's turning a series of copper wires that are inside of here. And when I do that, that's generating electricity. So what I'm going to do, but again, it's this whole concept of work. I have to do work to make that spin. So I have to exert a force through a distance. So it's kind of like lifting water up a dam or lifting up a building block or something like that. So I'm going to hook this up to the capacitor, okay? So I've got this thing hooked up, and then right now I'm going to disconnect this.
Is it from the shirts?
Oh, fantastic. Wow, these are okay. Wow, new rulers. How cool is that? Okay. No, you guys don't get these. Okay. Okay. All right. So, well, we're going to spend a whole unit on circuits, but for here again, here's a short version of the circuit. So, in this case, I'm going to have an LED light. I'm going to have a resistor. Okay, the resistor, what it does is that it impedes the flow of electricity. And then, but right now, this is not a complete circuit, so I've got this disconnected. So what I'm going to do is that I'm going to turn this generator, and I'm going to store energy in this capacitor. So when I do that, okay, I'm doing work because I'm exerting a force through a distance. And as I do that, I'm storing energy in that capacitor. Now, kind of like a dam, when you store water, if you open up the floodgates, that water is going to flow back down. So when I do that, and then I let go, that begins to spin a little bit on its own because that capacitor is trying to get rid of that excess energy. So I'm going to store this up, okay? Then we're going to stop it, and then we're going to disconnect it. So what I've done is that I've stored energy in this capacitor. So if I hook up my voltmeter now, by the way, that's a frustrating thing about electricity is they always like, if you've ever really worked with circuits, it can be a little bit frustrating. So right now, hold on. Okay, now I'm up to about 2 volts of energy that I've stored. So when I did that, I stored energy. I did work. Now I've got about 2 volts stored within that. So what I'm going to do now is that I'm going to hook that up and complete the circuit with this light. And it should have lit up. Hold on. Again, that's the frustrating thing about, especially with LED lights. LED lights only flow in one direction. There we go. Okay, so I've stored energy in that capacitor. So what's happening is that this is kind of like opening up the floodgates. So I've got water stored behind the dam, and what I'm doing is now I'm letting that energy, that water, flow out, and that's what's allowing that light to burn. So I'm not adding energy I'm not adding energy to the system. But what I've done is that I've done work. Okay, I've exerted the force through a distance. I've cranked the handle, I've stored energy. Now, what's going to be important in terms of electric fields is that I've done work. So what I've done is by doing that work, I've lifted up the electrons. So when you look at the equations for, and there's various ones, this is just the simplest one. So if you look at this equation, E equals epsilon naught Q over A. So epsilon naught is called the permittivity constant. It's rarely used. It has just one kind of application. This is about it. There's another one with the speed of light, which we'll get into later. So epsilon naught is just a number. It's on your yellow sheet, okay? It's just a number. Now, it has weird units. It's Coulomb squared over Newton meter squared. The reason that it has kind of these jacked up units is because it makes this work. So what this is telling me is the strength of the electric field within that capacitor, okay? So epsilon naught isn't going to change, okay? That's a fixed value. Q is the charge I'm going to put on there. And area, this is going to be the area of the plates. So if you look at what happens with the units, you have Q, which is going to be a charge in coulombs. You have epsilon naught, which is Coulomb squared over Newton meter squared. And then I'm going to multiply that by area, which is going to be meters squared. So then the meter squared cancels out. I lose one of the coulombs. The newtons flip up. Miracle of miracles, I get newtons per coulomb. Voila, that's what electric field is measuring. So in terms of physically what's happening, so when I was cranking that up, what I was doing, and here's a simple way to visualize this. Because it's a parallel plate capacitor, oddly enough, visualize this as two plates. And I'm going to have a negative side, just like on a battery. I'm going to have a negative side, and I'm also going to have a positive side. So imagine that I'm going to take an electron that's here, that's close to this positively charged plate. So you can kind of make the analogy of storing gravitational potential energy. So if I were to lift this electron up, why would I have to exert energy to get that electron to move up there? Yeah. So you have two things going against this. The electron doesn't want to go up towards the negatively charged plate because this thing is filled up with chihuahuas. And you're going, oh, really? You're going to make me go up there? No, I don't want to. Then, not only are you fighting that, but it's also attracted to, it's random, but it's like in your line of sight. So I've also got this positively charged plate here. So the electrons are going, dude, you know, it's just like you're making me run away from the St. Bernards, which I really like, okay? And then you're going to make me go towards the other chihuahuas. It's like, really? So you got to do work. You got to grab a hold of that chihuahua and lift that chihuahua up and move it closer to the other chihuahuas. Now, that's what I was doing when I was cranking that handle, right? I was storing energy. I was lifting the chihuahuas. Now, do the chihuahuas want to stay there? No. What do the chihuahuas want to do? They want to come back down to the St. Bernards, right? Now, when they do that, they're going to go, yip, 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 okay? They're going to have all this energy that they've got to get rid of. Guess what we do with that energy? We use it to make light, okay? So as those chihuahuas are returning back to the St. Bernards, we're using that energy to create light. So capacitors, and there's a whole bunch of, you can do it like a whole study on capacitors. How much charge they store, how fast they get rid of that electricity. There's a whole bunch, we'll spend a lot more time talking about capacitors. But there's a whole bunch of things you can do with them, and that's why they're so cool. So let's say, for example, you have your phone, right? You plug your phone in. Why do you plug your phone in?
charger.
Yeah, but what does that mean to charge? From an energy perspective, what does that mean?
Just for energy.
You're storing energy. You're lifting chihuahuas, okay? You're storing energy in capacitors, okay? Your battery. Batteries and capacitors work very much the same way. It's the same idea. You're storing energy. And that takes energy. So you can either plug that into the wall and let electricity do it, or God forbid, it's like, oh God, we don't have electricity. I need to charge my phone. Here you go. And it would work, okay? But it would work. It's like, what are you doing? Charging my phone, okay? Hold on, I can't hear you. Let me crank faster, okay? Right? So that's an option. It's like, you know, we lose electricity. Hey, want to charge your phone? Sell this to you. You know, might have to take a while, but you can do it. But that's what you're doing. So you've got your phone charged, right? And let's say that you want to take a selfie and it's dark and you need a flash, right? You need a flashing light, okay? Guess what? You have to have energy to make that flash of light work. That energy is going to come from the capacitor. So when you hit that button to create the light, to create that flash, what's happening is that energy is stored in a capacitor. So when you plug your phone in, you push the chihuahuas up. When you hit the button, you connected the circuit that allowed the chihuahuas to flow. The chihuahuas going, yip, 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 we're happy. And that sound of the yip, yip, yip is what you're using to make light. So obviously, you can only do that so often, and then guess what? The chihuahuas run out of energy. Guess what? You got to recharge the chihuahuas, you plug them back in. So that's the short version of how capacitors work. But here's the whole thing. So if you look at this, the whole key to this is this ratio of charge to area. So if you want a big electric field, what do you know about this ratio of charge to area? You want a big charge or a little charge?
Big.
Big charge with a
Small.
area. Okay? That's going to create the biggest electric field. Okay? All right, now, notice what isn't here is the distance between the plates. All right? That's the whole key. The distance between the plates isn't in this equation. We'll use that distance between the plates in other equations. It's just not in this one. So when you look at electric fields and you look at forces, so when you look at force, and this last assignment is going to pull all this together. So far, we could calculate force using FEC. Oh, here's the electric field times the charge, right? Which is a similar idea of force equaling mass times acceleration. You're going to have a certain electric field. The bigger the charge that you put in it, the more force that's going to feel. I have a certain acceleration based upon the size of this Earth. The bigger the mass that I put, the bigger the force is going to feel. Okay? Now, force can also equal kq1, q2 over distance squared. Oh, okay, so that's going to be the force between charged particles. Okay, so that's an option. Now, you can also set that equal to mg. So if you look at, I want to make a bead or something hover. Oh, the force either from the electric field or the force from the two charged particles could equal the force needed to make something hover. So when I was doing, you okay, Paige?
I just really had to sneeze. I'm being judged for it, apparently.
Oh, seriously, don't be judgy. It's Paige, come on.
My bad.
Really? Okay.
Such a chauvinist.
So, depending upon what you want to set things equal to each other, there's a whole bunch of different ways this can play out. So right before this point, F equals ma. Well, it can also equal kq1, so it can be the force between charged particles. It can be a magnetic field. It can also be, if you want to really go cosmic, it can also be m1, m2 over d squared. Wait for it. It can also tie in with springs where you have F equals kx. So at this point, there's a whole bunch of different ways that you can deal with forces. Charged particles, electric fields, springs, mass times acceleration, gravitation. So there's a whole bunch of different ways that that can play out. Keep this problem in mind when you look at the assignment. Okay, now, let's say Speaking of field,
Spring equals force. Ooh, okay, what about G-force with hamsters, huh? No, I didn't. You're the mole rat in G-force equals. Who's a rat for a mole?
If there's a mole, he's they're getting
so let's look at two different scenarios. I have a parallel plate capacitor, and I have a negatively charged plate, and I have a positively charged plate. And I have an electron, and the electric field between the plates is 500 newtons per coulomb, just to make up a number. So knowing that, could you calculate the force acting on the electron?
Yes.
Yes, wait a minute, what?
Multiplying them together.
Yeah. F equals EQ, right? So I could take that 500 newtons per coulomb. Now, what's the charge on electron? 1.60 times 10 to the negative 19th coulombs.
Yeah.
And I can get the value of the force by using EQ, right? So somebody give me this number. I just made that. Take 500 times 1.6 times 10 to the negative 19.
8 e to the 8 e to the
What'd you get?
17. 8 e to the negative 17.
Times 10 to the negative 17th newtons. Now, knowing that number, what can I calculate?
Gravity. No. Mass.
You know the mass.
What else is there to calculate then?
How about F equals MA?
Oh.
I'm just throwing that out there.
No, I don't think so.
No, what is this F equals MA?
No.
Seriously.
I didn't know that.
So,
I know, my bad. I failed US physics.
You can calculate-
3/4 of the way through and you're just learning about F equals MA?
You
Seriously.
messed it up that one unit for me.
Huh?
Remember when I had to look at how to F equals MA? Remember when I messed up F equals MA?
Oh, yeah. Yeah, that I about wanted to quit teaching at that point.
That was your fault.
So I can do, acceleration is force divided by mass. That's kind of cool. So 8.0 times 10 to the negative 17th newtons. What's the mass of a proton, or excuse me, of an electron?
something to negative 31st.
9.1.
9 something.
9 point what?
911 e to negative 31.
Okay,
Bam.
kilograms, right? So out of this, I can get my acceleration. So,
Very fast.
Brady, let me know what you get.
8.78 times 10 to the 13th.
Mach 23.
Almost faster than that owl.
Almost.
I did like the name of your troop, by the way. That was fun. Okay, now don't sit there and go, oh, that's faster than the speed of light. Okay, we're not going to accelerate this thing for very long.
2
Okay?
seconds.
It's going to be over a very short distance.
That's what I said.
But here's what I want you to look at. Okay? If I release an electron here from this side, as if I let go of it, what's it going to do? Is it going to move at all? If I have an electron here, okay, is that going to move? Is that going to want to move on its own accord up there?
No.
No, because you're not going to push. It's not going to move on its own accord to the other chihuahuas, right? However, if this was a proton, okay,
Dude, switch.
if this was a proton, would it move?
Yes.
Yes, because then it wants to go in that direction. So if I take that electron and put it up here, I've done work, I've lifted it up here. So if I have this electron up there, then that's going to be the acceleration of that electron as it goes across there. So knowing that acceleration, and if I know like that distance, I could go old school and use that equation. Like I could go v squared equals v naught squared plus 2ab. So if I know that that electron is lifted up here, and I know the distance between that plate, and I know, and I found that acceleration, I can figure out how fast that electron's going to be moving when it gets to the other side. Just like if I drop it, oh, here's a certain acceleration. So you can use those old school equations. Same thing would be true here. Now, here's what I want you to think through. If this was a proton, would a proton still feel the exact same force?
Yes.
Yes, because it still has the exact same charge. So a proton would feel the exact same force, okay? Would a proton have the same acceleration?
No.
No. What would happen to the acceleration of the proton?
It go down.
It would be less. Why?
Because
Bigger
it's
mass.
heavy.
Yeah, this has more mass. So if you release a proton, even though it's going to have the exact same force, it won't have the same acceleration because that proton is more massive, okay? But you can still do the same math and figure out how fast it's going to be going when it goes across. Okay, so stop that. So this assignment actually kind of has three different components to it. So on the sheet of paper, you've got the problems. There's no questions. These are just the problems from the book, 52, 54, 56, 60 through 62. That's part of the assignment. Then you have this problem that involves a spring. So there's two parts to the spring problem. The first situation, I tell you that here's a spring and it has an unstretched length. This is going to be important. The unstretched length is 4 centimeters. You're going to attach a 1 gram mass, which isn't very much, and it's going to stretch to 5 centimeters. So you can go from 4 to 5 centimeters once you add that 1 gram mass. You're going to use that to find the value of the spring constant. Remember, F equals Kx. So this is going to go old school, okay? So this is just another application of force. F equals Kx. You need to find the spring constant. Then we're going to take that same spring, and then we're going to lay it out, and then we're going to put like 2 charged beads on there, okay? Or like 2 negatively charged balloons, okay? You all have seen that. They're going to repel each other. So what's going to happen here is that this is going to stretch that spring out to 4.5 centimeters, okay? You want to use that information to find the charge on each bead, okay? So you have to find your spring constant first, then find the charge on each bead. Keep in mind the distances, okay? If you screw this problem up, do you use 1 centimeter? Do you use 4.5? Do you use 4? What do you use? So think that through. Then you also have this sheet. So on this one, you have 3 charges. Positive Q, 2Q, negative Q. What you're going to ultimately try and figure out is the net electric field at the origin. So I take you through this step by step by step. So number 1, I say determine the electric field created by Q directed towards O. So when you give this answer on number 1, I want the magnitude and I want the direction. You can either say right, left, positive X, negative X, I don't care, okay? Come up with a system. I'd recommend positive and negative. That's just me. Then you determine the electric field created by 2Q, okay? So 2Q is here. Remember, how do you define a positive, remember, you define the direction of the field based upon a positive test charge. Keep that in mind. Then when you get to number 3, the electric field created by negative 2Q. Then on number 4, determine the sum of the X and Y components at the origin. So what I want on question number 4, you're going to have a column that says, oh, here's all my X components. Mr. Burkhammer, here's all my Y components. This is the sum of these 2 values, okay?
17.
You could conceivably work it here if you write neatly and small, which negates that possibility for you. Some you can do that. Skippy, you could probably pull it off. Now, then, number 5, determine the magnitude of the electric field of the origin, which is basically one of these answers here. Okay? So I take you through this process step by step by step by step by step. The other two questions are just questions to answer. So you have three parts to this assignment. You have the book problems, you have the spring and beat problem, and then you have this. Okay?
There goes the-
I'm done. You're on your own. So here we go.
Happy birthday, you good guy.